Section 4.4 is about families of functions. Families of functions. What does that mean? It means, maybe you've had a teacher who talked about this before, all functions that have a certain type of formula, you might say. Here's a family of functions. F of x equals, let's make it a two-parameter family of functions. Ax times e to the negative bx. A and b are constants, but they could be any constant. I could even allow them to be negative constants if I wanted to, though for most applications of this function, you would want them to be positive constants. Though do look at the fact that I have a negative sign in front of the b here. So if b is a positive constant, then negative b is a negative constant. So I'm going to go ahead and assume that a and b are positive constants. I'll write that like this. It's a two-parameter family of functions. Technically speaking, my notation that I'm using here is not ideal because just writing one symbol f of x makes you think, oh, this is one function. And certainly if a and b were fixed numbers, then it would be one function. But it's useful to think of this as representing infinitely many functions, one for the infinitely many possible values of a and b, one function for each possible value of a and b. And when I think of it that way, I like using subscripts, and you should feel comfortable with this too. The book doesn't always do this, if at all. I like writing f sub a comma b of x equals ax e to the negative bx, just to emphasize that I've got one function for each possible value of a and b, ultimately meaning I've got infinitely many functions I'm thinking about. I'm going to think about this collection of infinitely many functions all at once. Isn't that amazing? Calculus gives you the power to do so. Let's do so. What would we be interested in? Probably its graph. Probably applications, though I'm not saying any applications at the moment. I do happen to know one example of an application of this is to probability and statistics. You can encounter functions similar to this. A and B can't be anything in such an application, but they do come up. Are there other applications? Probably in physics. I imagine there's some applications of functions like this. I don't know of any particular applications offhand, but they probably do come up in physics and engineering. This is what I write. That's just me personally, but you should feel comfortable if you see me write this on an exam, for example. What does the graph look like? Do the same thing you always do. Try to find critical points. See if they're maxes or mins. Find inflection points. Possible inflection points at least. Take the derivative. I'm going to go ahead and keep the subscripts there. You should feel comfortable doing that as well. Do you have to do that for your homework? Probably not for your homework because the textbook doesn't do that. But you'll see on old exams, sample exams, I sometimes use the subscripts. You should feel comfortable with that. Treat the A and B as constants, but the formula depends on them. So that's why I have them as subscripts. Just to emphasize that they are there. This is the product of two functions. I need the product rule. A left function a times x and a right function e to the negative bx. Left d right with the derivative of the right function. I need the chain rule as well, giving me an extra factor of negative b. I hope you feel comfortable enough now with the chain rule that I can do that fairly quickly and not completely explain it. That's the benefit of practicing for a gateway exam, hopefully. Left d right plus right e to the negative bx times the derivative of the left, which is just a. There's the derivative with respect to x. We want to figure out where this is 0 to find critical points. Set this equal to 0 and solve for x. It's almost always a good idea to factor out any common factors. In both terms, there's a factor of a, and there's also a factor of e to the negative bx. Factor those out. What's left over from the first term is a negative b times x. What's left over from the second term is 1, right? You don't see a 1 there, but you could pretend it's there. I'll erase that now. A is positive, so that's not 0. E to a power is never ever 0. So the only way this is 0 is if negative bx plus 1 is 0. In other words, bx equals 1, so x equals 1 over b. That is the critical point. Ignore this mark right there. That's the critical point. Is it a local max or a local min? Or neither? We need either the first or second derivative test. Probably simplest to use the first derivative test, because the first derivative is nice and factored here. As the product of two things, I need to think about the sign of this, plus or minus. I could draw a number line. In fact, drawing number lines like this is effectively the way that I want you to show your work when you use the first derivative test. Mark off the critical points. There's only one of them. Now test numbers on either side of this. That seems a little tricky here because, like, what is b? You don't have to know what b is to test numbers on either side of this. You do know half of this would be on the left side of it. 1 over 2b, for example, would be to the left of 1 over b. Plug that into the derivative. Really? Do I have to? Not literally, just in your mind. A is positive. E to the negative bx is positive. What about this one? If I replace x with 1 over 2b, what happens? Multiply. Negative b times 1 over 2b. The b's cancel, leaving me with negative 1/2. Plus 1 is positive 1/2. This is positive. F prime of that is positive. Plug in a number over here. How about like 2 over b? 2 over b is twice as big as 1 over b. Positive, positive. You plug in 2 over b here for x. Negative b times 2 over b. Once again, the b's cancel. You get negative 2 plus 1, negative. Actually, I usually put these below the number line. F itself must be increasing here and decreasing here. So it's got to be a local max at this critical point, as long as b is positive, evidently. This function is defined for all x. I could have actually also plugged in negative numbers into the derivative here, like negative 1, and gotten a positive number here. If x is negative 1, negative b times negative 1 is positive b, plus 1 is positive. I could have done that as well. In fact, it's a global max at 1 over b. The graph, well, we might wonder whether there are any inflection points as well. Let's do that. Let's find f double prime. I'm going to continue to use subscripts, and you should feel comfortable doing so if I ask you to. Take the derivative of this. Should I use the factored form or this form? It doesn't really matter. Maybe the factored form is easier. I can use the product rule. Left d right. The derivative of b negative bx plus 1 is negative b. That's simple. Left d right plus right d left. The derivative of the left, I need the chain rule for. I'll get an extra factor of negative b, and that's being multiplied by right, negative bx plus 1. So I quickly use the product rule there. Hopefully no mistakes. There's a common factor of a and e to the negative bx, and in fact, even a negative b that can be factored out. Negative ab e to the negative bx can be factored out of both of those terms. What's left over is a 1, and then this thing, minus bx plus 1. This thing simplifies to 2 minus bx. set this equal to 0 to solve for possible inflection points where the second derivative changes sign. This part is never 0, so this means 2 minus bx is 0. So x is ultimately 2 over b is your possible inflection point. Is it really an inflection point? Yes, it is. The second derivative does change sign. You could think about the sign of this. And actually, when x is less than 2 over b, because of that negative sign in front, the second derivative is going to be negative. And when x is bigger than 2 over b, the second derivative is going to be positive. So the graph increases to a maximum at 1 over b, and then changes from concave down to concave up at 2 over b. I also can look at the formula and see if I plug in 0, I get 0, right? If x is 0, I get a times 0 times e to the 0 is 0. The graph goes to the origin here. That's its x and y intercept. It looks about like this. And as x goes to infinity, this graph does go towards 0. It turns out, though, we haven't proved that. Because effectively, you have a power function times an exponential decay. This is getting big as x gets big, but this is getting close to 0 as x gets big. And the exponential decay wins out, dominates, so to speak, as far as how fast it goes to 0. Enough to make this entire graph go to 0. Said that kind of fast, but it is true, and you can check on your calculator. We're actually, later this week, going to be able to use L'Hopital's rule to verify this goes to 0 as x goes to infinity. If you've ever heard of L'Hopital's rule before that. Coming up later this week, probably Friday. Yeah, this is what it looks like. If we were after the global max value, remember when I say put the word value on that, global max value, that means find the output of the maximum. What's the second coordinate of that point? Plug the critical point into the function. Not the derivative, not the second derivative, but the function. And here's what you would get. Simplify this. The b's there's cancel. Looks like you get a over b e to the negative 1. Or if you prefer, a over e times b is the global max value. It's got to depend on a and b, right? These things all have to depend on a and b because I haven't said what a and b are. But I have effectively solved infinitely many problems at once here. I found the global max location and value for these functions, no matter what a and b are. If I happen to know a and b, I can then plug b into this equation to find the x value where the global max occurs, and this equation to figure out where the inflection point is. And I can use this formula to find the output for the global max. That's super powerful. Infinitely many problems solved all at once. That's pretty astonishing if you think about it. God has given you the power to solve infinitely many problems in one fell swoop when you do this kind of thing. Let's go back to free fall. Got a ball under the influence of gravity. The force due to gravity is got magnitude m times g, where m is the mass and g is the acceleration due to gravity. It is in the downward direction. And it turns out the height as a function of time, I'll call the height y because that's what the book does, is, well, if you use g equals 9.8 meters per second squared, turns out the height is negative 4.9 t squared plus the initial upward velocity v naught times t. You can say v sub 0, or you can say v naught, not v naught, but v naught. It rolls off the tongue a little bit nicer, and it's fun to say. V naught, the initial upward velocity. Why am I calling it the upward velocity? Because if you throw the ball upward at first, you want the initial velocity to be positive. So v naught being positive means you throw the ball upward at first. If V naught is negative, then you throw the ball downward at first. If V naught 0, then you're letting the ball go from rest. Plus the initial height, y naught. Really, this is a function, a two-parameter family of functions. V naught and y naught are your parameters. I could use a subscript here, V naught comma y naught. I couldn't really fit it very well there. This would be a better way to write it. I could use subscripts and go from there in the same kind of way as before. The book doesn't do that. And I think for this example, I will not, except right there. What does the graph of this look like? Well, it's going to be a parabola, right? Because it's quadratic. In fact, it's going to be downward opening, concave down, because the coefficient of t squared is negative. But what would be most interesting for us is figuring out maximum. How high does the ball go? What time does that occur? And maybe even the t-intercept. Though no calculus is necessary for that, you would need algebra, quadratic formula. Let's figure out the maximum first. dy dt equals f prime of t will be the velocity. I could call that v if I wanted to. That'll be the upward velocity, positive when it's moving upwards, negative when it's moving downwards. And yes, I could include the subscripts, but I'm not bothering to do that right now. Take the derivative, negative 9.8t plus v naught. That's a one parameter family. The initial height doesn't affect the velocity. Well, that makes sense. If you're near the surface of the Earth, it should not affect the velocity. If you're far away from the surface of the Earth, it can, because technically g is not really constant. I think I mentioned that before. You go up a mountain or into space a little ways, g is smaller. So this is only an approximation near the surface of the Earth, and it also assumes no air resistance. But if I set this equal to 0, I can solve for the value of t, where I'm going to be at the maximum height. Add 9.8t to both sides, and effectively I swap the sides. Divide both sides by 9.8. T seems to be v naught over 9.8. That's solving infinitely many problems at once. That's telling you the time when the ball reaches its maximum height in terms of the initial velocity. I can plug in any initial velocity into that to find the maximum height. Time for the maximum height. What's the maximum height itself? I'd have to plug this into the function itself. And by the way, it's your critical point, and it will be a maximum because we know graphs of things like this are downward opening parabolas. This is at v naught over 9.8, v naught over g. Plug that into the function to find the max height. F of v naught over 9.8. Yeah, it's a bit of a pain, but just do it. Replace t with v naught over 9.8. Everywhere you see a t, simplify. I guess I'd get this. And maybe I should combine these two fractions into one by getting a common denominator of 9.8 squared. Not that you have to do that, but maybe it's nice. If you wanted to do this more generally, instead of a 9.8 and a 4.9, you could have a g here and here, and this would be a G over 2 right there. And that would then apply also if you were on the moon or some other up at the top of a mountain, and G's a little smaller than 9.8. That'll be the maximum height above the ground. It's really kind of like, it's like a function of V naught, isn't it? Being a function of V naught, I guess you could even graph this thing. Well, you have to know what Y naught is as well. Or maybe you want to think of it as a multivariable function of V naught and Y naught. Graph the multivariable function. You could. I won't, but you could. You could try to understand that graph with level curves, contour map, all the level curves. You could try to calculate partial derivatives of this thing to figure out how it changes as V naught and Y naught changes. And that would be physically interesting to know. How does small changes in V naught affect the maximum height? That would be an interesting thing to know. Use the derivative of this with respect to V naught. As far as when it touches the ground again, what's that intercept there? Use the quadratic formula is the best thing. Set this equal to 0 and solve for t. I'll rewrite it down here, negative 4.9 t squared plus V naught t plus Y naught equals 0. Quadratic formula is going to give t equals negative b is negative V naught plus or minus square root of b squared minus 4 times a times c is the coefficient of the constant term, which is really Y naught, over 2 times a. And which one of these is going to be positive? Well, you got V naught, negative V naught divided by negative 9.8. That's really positive V naught over 9.8. You'd really want to take the plus one then. Well, okay, you got a negative in the bottom. Actually, you take the minus if you think of the bottom as negative 9.8. If I do that multiplication, I get 19.6. Anyway, that'll be the location of the positive root of this thing. 2 minuses make a plus here. Those negatives can cancel. I guess I will go ahead and cancel them. That would be the positive root. That would be the time that it hits the ground. Once again, it's a function of V naught and Y naught. It's a multivariable function that you could graph and that kind of thing. I won't take the time to do so. You could plug numbers in too. You should be able to, on the exam, plug numbers in if I gave you a problem like this. But you should also be able to think more generally about this stuff as I've just done.